Mastering Algorithms from Scratch, a journey through essential tutorials. Welcome to your definitive exploration of algorithm fundamentals. This guide offers structured learning paths designed to take you from novice status to confident problem solver using modern teaching methods. If you've ever struggled with understanding big O notation or implementing sorting algorithms, you're exactly who this material was created for. We'll break down complex concepts using clear examples anyone can understand. The algorithmic mindset. Understanding algorithms requires developing a new way of thinking about problems. You begin by identifying patterns in how things work, rather than focusing solely on individual components. This mindset shift allows programmers to approach challenges systematically. When debugging, instead of trying random fixes, an algorithmic thinker examines the core logic driving unexpected behavior. Breakdown. First, divide complex tasks into smaller, manageable subproblems before attempting solutions. Look for repetition. Identify common operations that appear multiple times within similar context. Fundamental building blocks before diving into advanced techniques. Master basic elements that form the foundation of every algorithm. These include control structures and primitive operations fundamental to computational thinking. Mastery of loops, conditionals, and arithmetic operations enables efficient algorithm development. Understanding variable scope and data types prevents common implementation errors early on. Data structures overview. Proper use of data structures dramatically affects algorithm performance. Arrays offer fast access at cost of insertion speed, while linked lists provide flexible memory allocation. Choosing right structures depends on expected usage patterns. Hash tables enable rapid lookups while binary trees maintain ordered element relationships efficiently. Sorting and searching essentials. Sorting forms the bedrock of many computer science applications. Different algorithms excel depending on dataset size, memory constraints, and stability requirements. Quicksort offers optimal average case performance but has worst-case degradation scenarios. Merge sort guarantees consistent efficiency at expense of higher space complexity. Stable versus unstable sorts. Some algorithms preserve original order of equal elements, stability, in-place modification. Certain implementations rearrange existing storage without extra memory. Dynamic programming foundations. This powerful technique solves optimization problems by breaking them into overlapping subproblems. Solutions to these smaller pieces get cached and reused across calculations. Possible states represent partial solutions toward ultimate goal. By remembering previously computed results, redundant computation gets avoided dramatically. Optimal substructure. Optimal solution contains optimal solutions to its subproblems. Overlapping subproblems. Subproblem computations occur repeatedly during recursion tree traversal. Greedy algorithms. Explained. A greedy strategy makes locally optimal choices hoping overall result remains globally optimal. While effective for some problems, it often fails where dependencies exist between decisions. Coin change examples demonstrate both effectiveness and limitations. With coin denominations 1, 3, 4, greedy choice may produce non-optimal solution for certain amounts. When greed fails, not all optimization problems respond well to greedy approaches. Classic counterexamples include minimum spanning tree with arbitrary weights and activity selection scheduling conflicts. To determine suitability, consider whether future decision impacts depend only on current state. If later choices cannot affect previous outcomes, greedy method shows promise. Backtracking techniques used extensively in constraint satisfaction problems. Backtracking explores possible solutions incrementally, discarding paths that violate constraints. N-queen puzzle exemplifies this approach perfectly. Program attempts placing queens row by row, abandoning. Configurations creating conflicts promptly. Depth-first search, common traversal pattern employed to explore complete solution spaces. Exhaustively pruning. Early elimination of obviously invalid branches reduces unnecessary computation significantly. Graph traversal algorithms. These algorithms explore nodes connected via edges, forming backbone for network analysis, route finding, and social media friend recommendations. Breadth first search, BFS, discovers nearest nodes. Depth first search, DFS, follows deep connections until end reached. Dijkstra's shortest path algorithm based on relaxation process improving tentative distances iteratively. Dijkstra finds shortest paths in graphs containing only positive edge weights. Priority queue maintains unprocessed nodes sorted by current best estimates. Repeated extraction leads naturally to optimal solution discovery. Advanced topics exploration. Having mastered fundamentals, now venture into cutting-edge areas like divide and conquer strategies, string matching algorithms, and randomized techniques. Quick select algorithm adapts quicksort principles for median finding without full array sorting. KMP algorithm improves upon naive string searching with linear runtime guarantees. Practice makes perfect. No matter how much theory you absorb, hands-on experience remains vital. Implement algorithms manually to truly grasp their inner workings. Create small projects solving real-world puzzles. Try generating maze solvers or optimizing travel routes using learned techniques. Conclusion: you've embarked on transformative journey exploring algorithm essentials. From basic building blocks to sophisticated strategies, this progression equips you for diverse computing challenges ahead. Continue honing skills through daily practice. Remember that mastery comes not from memorization, but from repeated application and adaptation to novel situations.